Hello, my name is Marta Ulloa. I am a PhD student at the University of Florida, and I'm happy to give you all this talk. The name of the talk is The Standard Model CP Violation is Enough, and this is a talk based on my most recent work, together with Gilly Eller, Rachel Houts, who is my advisor at the University of Florida, and Shada Ipek. So, one of the most intriguing questions on physics is why do we end up with more matter than antimatter? And a way to answer this question is going through the charge parity violation that we get from the standard model. So first of all, let's go and see like a little bit of the history of the universe. So after the Big Bang, the universe went through a phase of inflation. After this inflation, where the universe was very hot, the universe started to cool down. And as the universe was cooling down, it went through some phase transitions. So we can go through the first one, and we can go there was some grand unification transition, then like electroweak transition, which happens to be important because here is where the particles acquire mass, and then through the Higgs mechanism, after this, we can go through hadronization, where some protons and neutrons are going to be formed. After this, we go through nucleosynthesis, where the light elements are being created, such as deuterium, helium, and lithium. After this, we got like matter domination, recombination, galaxy formation era until today. The mechanism that I'm going to be talking today is a mechanism within baryogenesis. Baryogenesis aims to explain this asymmetry that we observe between matter and antimatter. But mesogenesis, that is trying to approach to this question working on low energy scales, because from these low energy scales, we can maybe attempt to see some signals on the experiments. So again, the mechanism for the mesogenesis is going to happen between hadronization and Big Bang nucleosynthesis. And in this timeline, we can see at what temperature of the universe these transitions were happening. So back in 1967, Sakharov proposed these three conditions that any baryogenesis mechanism complies. Our mesogenesis mechanism will also comply with these three conditions. So the first one is the out of equilibrium. So we have the decay rates from the V mesons that we want this to be out of equilibrium to avoid any compensation between processors, such as baryons annihilating with antibaryons. So we require out of equilibrium of this process. Then we're going to have CPB violation, and then we're going to end up with some baryon number violation. This means we're going to end up with some excess of baryons, which is the normal matter, over antibaryons. So the standard model explains this CPB violation through the CKN matrix, which is a matrix that is containing the quarks, and then these quarks go through some interactions, and these quarks on the weak sector are going to change some flavor. We're expecting this matrix to be unitarity, but it is not. So this non-unitarity of this matrix is giving us some charge parity violation, and one way to express this is the Jarlskog invariant, which is something of the order of 10 to the minus 5. Even though the standard model contemplates some charge parity violation, is not enough to account for the amount of asymmetry that we can observe in the universe. So we need to look for other mechanisms. In this case, mesogenesis is going to require a dark sector, and with this dark sector, it will also need a dark sector mediator. Our proposed mechanism will use dark sector dynamics, and we will propose that this decay rate is happening through a massive mediator Y that is going to depend on the temperature, and it's going to shift masses from one phase, from the hadronization phase towards all the way down, all the way up to Big Bang nucleosynthesis. So another way that we have from the standard model to measure CP violation is through the semi-leptonic asymmetries, which is the decay rate. We can focus here in the semi-leptonic asymmetries, that there is a way to calculate this from the standard model in a theoretical way. These numbers that I'm showing here are the theoretical values, not the experimental ones. So we're measuring the decay rates of these B mesons. So we have the S system and the D system. So we can see in this picture that I lifted from one of the original papers, 3-thin-B Mesogenesis, how the black box is where these values are on the standard model. And then we can see how if we add a dark sector to baryogenesis, we can expand the parameter space where we can look for these semi-leptonic asymmetries. So one important thing to see here is that the semi-leptonic asymmetry for the D system is negative. Meanwhile, for the S system, it's going to be positive. So this negative asymmetry coming from the BD system is going to decrease the baryon asymmetry on the universe. So this is going to play a role in the mechanism I want to explain here. So this is, we can measure like the asymmetry through the entropy ratio, the baryon and the density baryon entropy ratio, which is measured to be 8.7 times to the minus 11. We can rewrite this expression as the second in this slide. And here we have some branching fraction. This branching fraction is the one coming from the B mesogenesis mechanism, where it was proposed that this neutral B meson is going to decay into an anti-baryon and a baryon on the standard model. So this branching fraction will have some collider constraints. These constraints are coming from how the experiments are looking for these branching fractions. And when they are looking for this, we realize that there is some missing energy on the results. So there was proposed that this missing energy could be explained through dark sector. So this is going to be multiplied by the semi-leptonic asymmetry, which is measured from or predicted by the standard model to be 10 to the minus 5. And we're going to be multiplying by another factor that comes from solving the Boltzmann equation, which could vary from 0 to 1.4, depending on the temperature. And this value comes from the coherent oscillations between the decay rates of these B mesons. So the V mesogenesis mechanism, as I said before, complies with the Sakharov conditions, and we can see here in this diagram how this happens. So we have a scalar particle that is going to decay into an antiquark and big quark. So we can see how after this happens, we're going to have like some B mesons. So these mesons, neutral B mesons are going to go through some oscillations, and these oscillations will produce the violation on baryon number that we see today. So we're going to have some that go to an antibaryon in the dark sector and a baryon in the standard model. So the Lagrangian that we're using for this mechanism is given in this equation. So we can see here how we have the Yukawa couplings, and we have like this morphon, which is the Y that we have here, how this morphon is going to help with the interaction between the dark sector and the visible sector. This morphon is going to have some constraints. So it has to be color triple scalar. it has to have electric charge -1/3 and a baryon number -2/3. This is going to be identified with an S quark. And then at the same time, since we're identifying this morphon with an S quark, it's going to give like some other constraints. So because we want to work in an effective theory, we're going to integrate this morphon out of the Lagrangian, out of this, and then we're going to obtain an effective operator that is going to be describing the mechanism. So the searches for the S quarks will constrain the Wilson coefficient that we're going to obtain. Therefore, the mass will have to be heavier than a few electron volts for this morphon. And then at the same time, we have some kinematic constraints. We have the dark sector baryons that have to be less than 1 gigaelectron volts, just because we want to avoid any kind of issues with Big Bang nucleosynthesis. And also we have some channels such as 5B UDD that is going to be forbidden by proton decay constraints. So in this slide, we can see how we end up with this effective 4 Fermi operator. So we can also see some of the possible decay into some baryons in a dark sector for these systems, for the BD system and the BS system. And just like to see just like to see how this morphing mediator is going to mediate the interactions between the standard model quarks and the dark sector. So in this figure, again, we have the mechanism that I am talking about. And then here we can see clearly how the Y morphon is interacting on the dark sector, ending up with antibaryon and then some part on the standard model. So to have to show some of the parameters that we need to have for this successful baryogenesis. So as I said before, the semi-leptonic asymmetry plays an important role to achieve this. So since the semi-leptonic asymmetry for the system V is negative, we don't want this process to dominate, because otherwise we're going to decrease the generated asymmetry. So we don't want that. So we can have like the opposite case where this is completely turned off, and then we have the other system, the S system, to be to have like the particle completely decaying into the BS system, which is going to enhance the process that we want to show. So this is like the maximal possible enhancement rate of this branching fraction. So we can see how we can go from 10 megaelectron volts up to 17 megaelectron volts, and how the mass of this morphing mediator is changing as the temperature changes. So the next case that I can show you is that we wanted to show is when we have these branching fractions between the S system and the D system happening at 50% rates. So in this case, the baryon asymmetry of the universe can only be generated for higher values of the temperature. So we can see how this could be achieved by having like 15 to 20 megaelectron volts. And we can actually also see how these coherent B oscillations are going to be highly suppressed when the temperature hits 70 megaelectron volts. And again, like in the Y axis, we can see how the mass of this morphon is varying from 100 gigaelectron volts all the way up to 400 gigaelectron volts. So finally, we wanted to focus on an example for this. So we choose this potential, which is a morphon scalar potential, because we wanted to show, and I'm going to show in the next slides, example of domain walls for this potential. So we can see here how the mass of this morphon field were given, like it's going to go from 100 gigaelectron volts when this potential is in a false vacuum, and it's going to happen a phase transition from this false vacuum to a true vacuum, and it's going to go all up to 1.2 teraelectron volts. So the conditions for this to happen is that the temperature, sorry, the mass of the morphon will have to shift after achieving the baryon asymmetry that we observe in the universe. So we will have 1 gigaelectron volts, and then it will have to shift after BAU. Then we will need to have percolation, so because we need to transition from the false to the true morphon vacuum. And finally, we need to avoid inflation because we don't want to trigger any other phase of inflation of the universe, so we need to avoid this. So in this picture, we can see like the example that I'm talking about. So we have that the mass of the morphon is going to start with 200 gigaelectron volts, where it's like in the false vacuum, and then it's increasing all the way to 1.2 teraelectron volts when it finally goes to the true vacuum. So the morphon field will fall into patches of true and false minima, forming a network of domain walls that will eventually annihilate. The mass of the Y is going to be smaller in the false vacuum and larger in the true vacuum, and we require that the domain wall network will safely disappear. So this will, domain walls will have to annihilate at a temperature around 10 megaelectron volts. This will happen before Big Bang nucleosynthesis. And then the domain walls must avoid dominating the energy density of the universe to trigger, because this will trigger inflation. So finally, this phase transition of this morphon field will trigger, will potentially generate like some stochastic gravitational wave signal, which we can try to look for. So for this picture, to generate this picture, we use the potential that I showed before, and then we were setting some parameters in our paper. You can see the benchmark for these parameters, and then we vary this scalar to like some values until we were able to see some crossover of this signal, the peak of these signals with some of the experiments nowadays. Like these lines for these experiments are future signals that are expected from these experiments, except with nanograph. And well, just like some future directions in our work. So there is so much that we can do with this proposed mechanism. So one of these directions that we could take is explore the dark sector phase transition, but in our relays, taking into account like an inflationary context. Also, we can maybe explore the dark sector with multiple morphon fields, or like in this like dark sector dynamics, we can also like try to look for confining phase transitions with large number of dark quark condensates, or even like change the morphon mediator. So instead of being an scalar, try to make this morphon mediator a vector field. And this is everything that I have to say for this talk. Thank you so much for your time, and I hope you enjoy this talk. Thank you.